Hello everyone, and welcome to Dr. Carminati's YouTube channel. We are absolutely delighted to have you here today as we embark on an exciting journey into the world of the approved Federal Information Processing Standards, or FIPS, for post-quantum cryptography. Specifically, we're diving deep into NIST FIPS 203, a groundbreaking document that's shaping the future of digital security. If you're new to my channel, I'd love for you to hit that subscribe button, give this video a like, and share your thoughts in the comments below. Your participation fuels this community, and I can't wait to hear what you think as we explore this fascinating topic together. So let's jump right in. Today, we're tackling a subject that might sound intimidating at first: post-quantum cryptography. But don't worry, I'm here to guide you through it step by step, as if we're chatting over a cup of coffee or tea. Whether you're a complete beginner or someone with a bit of tech know-how, I'll make sure you leave this video with a clear understanding of what FIPS 203 is, why it's a big deal, and how it connects to your everyday life. By the end, you'll see why this document from the National Institute of Standards and Technology, or NIST, isn't just a technical milestone, it's a shield for our digital future. Let's start with the basics. Cryptography is all about keeping information safe. Picture it like locking your house to protect what's inside. In the digital world, cryptography secures your passwords, your credit card numbers, your emails, pretty much everything you do online. For decades, we've relied on systems like RSA and elliptic curve cryptography. These methods use challenging math problems, like factoring gigantic numbers or solving discrete logarithms, that traditional computers can't crack without spending centuries on the task. They've served us well, keeping hackers at bay and ensuring our online transactions stay private. But there's a storm brewing on the horizon: quantum computers. What makes quantum computers so unique? Unlike the computers we use today, which process information in bits, those familiar zeros and ones, quantum computers use something called qubits. Thanks to the weird and wonderful rules of quantum mechanics, qubits can exist in multiple states at once, a phenomenon called superposition. They can also entangle, linking their states in ways that let quantum computers perform calculations at mind-blowing speeds. Does this mean those tough math problems underpinning RSA and elliptic curve cryptography? A powerful enough quantum computer could solve them in days, hours, or even minutes. Suddenly, the locks we've trusted for years could get picked wide open, exposing our data to anyone with the right tech. That's where post-quantum cryptography comes in, a new generation of encryption designed to withstand quantum attacks. Scientists, mathematicians, and cryptographers have been working tirelessly to create systems that stay secure even when quantum computers arrive. Leading this charge is NIST, a U.S. government agency that sets standards for everything from timekeeping to cybersecurity. After 8 years of intense research, collaboration, and competition, NIST released FIPS 203 on August 12, 2024. This document isn't just a collection of equations. It's a battle-tested plan to protect our digital world as technology leaps forward. So let's unpack what's inside and why it matters to all of us. The official title of FIPS 203 is Module Lattice-Based Key Encapsulation Mechanism Standard. I know it sounds like a sci-fi gadget, right? Let's break it down into bite-sized pieces. The authors at NIST, a team of cryptography experts, focus on a specific tool called a Key Encapsulation Mechanism, or KEM. Think of it this way: if you're sending me a secret message in a locked box, I need the key to open it. A KEM is the process of wrapping that key in a secure package and getting it to me safely. The module lattice-based part tells us how it works. In math, a lattice is like an infinite grid of points stretching out in all directions. The security of this KEM comes from lattice problems, such as finding the shortest distance between 2 points on a grid so complicated that it's practically a maze. These problems are challenging for regular computers and, crucially, for quantum computers too. The star of FIPS 203 is an algorithm called ML-KEM, short for Module Lattice Key Encapsulation Mechanism. It's built on an earlier concept called Crystal's Kyber, which came from a global effort to find quantum-resistant cryptography. Imagine a worldwide contest where the brightest minds submit their best ideas. NIST kicked off this competition in 2016, and over the years, they whittled down dozens of proposals through rigorous testing, kind of like a cryptographic version of Survivor. Kyber stood out for its strength and efficiency, and the NIST team refined it into ML-KEM, making it the first standardized post-quantum KEM. The authors didn't just pick a winner. They polished it into something federal agencies, businesses, and eventually all of us can rely on. So how does ML-KEM actually work? Let's walk through it with a simple example. Say you want to send me a confidential file, like a digital treasure map. MLKM starts by generating two keys for me, a public key, which I can share with the world, and a private key, which I guard with my life. You take my public key and use it to create a shared secret, a random string of numbers that only you and I will know. MLKM scrambles that shared secret using lattice math, turning it into a ciphertext, a jumbled mess that's meaningless to anyone else. You send that ciphertext to me, and I use my private key to unscramble it, revealing the shared secret. Now we both have the same secret, and we can use it to encrypt and decrypt the file. The lattice problems ensure that even a quantum computer would struggle to break in, while the modular design, think of it like Lego blocks, keeps the process fast and flexible. Why should you care about this? Because this isn't just for tech geeks or government spies. It's going to touch your life. FIPS 203 is mandatory for federal agencies, so systems handling everything from tax records to national defense will switch to MLKM. But the ripple effects go further. Tech companies, software developers, and hardware manufacturers often follow NIST's lead because these standards set a global benchmark. In a few years, when you're shopping online, video chatting, or checking your bank balance, post-quantum cryptography could be quietly protecting you from quantum threats. It's like upgrading the locks on every digital door, ensuring they hold strong no matter what tools thieves bring. Let's zoom in on the document itself. FIPS 203 runs about 30 pages, and it's a treasure trove of detail. The NIST authors spell out every step of MLKM, how to generate keys, how to encapsulate and decapsulate them, and even how to test the system to confirm it's working. They include tables of parameters, things like key sizes and security strengths, so developers can tailor the system to different needs. For instance, they define 3 security levels. Level 1 offers solid protection, Level 3 ramps it up, and Level 5 is the Fort Knox of encryption, all based on how complex the lattice problems are. They also throw in pseudocode, simplified instructions for programmers, and tips for implementing MLKM efficiently. It's a practical guide, not just a theory, and that's what makes it so powerful. Speaking of power, MLKM isn't just secure, it's fast. The NIST team made sure it ran smoothly on real-world devices, from servers to smartphones. Encryption can't bog down your tech, or it's no good in practice. Imagine if every website you visited took ages to load because the security was too heavy. MLKM strikes a balance, delivering top-notch protection without sacrificing speed. That's one reason it won NIST's competition. It's not just a lab experiment, it's ready for the real world. The authors highlight this efficiency, showing how MLKM's modular structure lets it scale up or down depending on the job. Let's take a quick detour into how we got here. Back in 2016, NIST called for submissions from cryptographers worldwide. Picture hundreds of brilliant minds tossing their hats in the ring, each with a unique take on post-quantum security. Over the next 8 years, NIST tested these ideas, poking holes in them and refining the best ones. They faced attacks from researchers, simulated of course, to see what held up. MLKM, rooted in Kyber, survived the gauntlet and emerged as a champion in 2022. The FIPS 203 authors finalized it in 2024, adding the polish needed for official use. It's a testament to teamwork, persistence, and a shared goal, keeping our data safe as quantum tech looms. But FIPS 203 isn't the whole story, it's part of a trilogy. NIST also released FIPS 204 and 205, which tackle digital signatures, another critical piece of cryptography. Signatures prove who sent a message, like a digital wax seal. Together, these standards form a robust toolkit for the quantum era. And there's more to come. NIST is working on a 4th standard, based on an algorithm called Falcon, to round out the signature options. The FIPS 203 authors nod to this bigger picture, framing MLKM as the first step in a long-term strategy. It's like they've laid the foundation for a quantum-proof house, and now they're building the walls and roof. If you're new to this topic, here's what I want you to take away. Quantum computers could one day crack our current encryption, but we're not sitting ducks. FIPS 203, crafted by NIST's expert team, gives us MLKM, a tool to lock up our data so tightly that even quantum machines can't break in. Whether you're a student curious about tech, a professional in the field, or just someone who loves learning, this matters because it's about protecting the digital world we all share. It's not science fiction, it's happening now, and it's going to shape how we live online. Before we wrap up, let's reflect on the human side of this. The authors of FIPS 203 aren't just names on a page. They're people who've spent years wrestling with complex math to solve a real problem. They've collaborated across borders, debated late into the night, and poured their expertise into this standard. It's a reminder that technology isn't magic. It's the result of hard work and ingenuity. And now it's in our hands to understand it, use it, and maybe even build on it. I hope this deep dive into post-quantum cryptography and FIPS 203 has sparked your curiosity. Maybe you're surprised by how close quantum computers are, or perhaps you're excited about lattice math. Who knew grids could be so cool? Drop a comment below and let me know what stood out to you. If you enjoyed this video, give it a like. It helps more people find this content. And if you want to stick around for more explorations like this, hit that subscribe button. I've got plenty more to share, and I'd love for you to join me on the journey. Thanks for spending this time with me today. I'll see you in the next video.